In this video, we're going to look at complex power and try to relate that to a circuit in Phasor domain and try to see if we can come up with additional relationships that we could use to solve problems and analyze circuits. So what we're going to do, we're going to start by kind of taking a drawing of a circuit. Let's say we have a device, a circuit if you will, and we know that the circuit has an impedance of Z. And we are in Phasor domain, so we will have I effective, which is basically the maximum is divided by I effective in Phasor domain is basically I of max divided by square root of 2. Effective was the RMS if you remember, and then the voltage would be voltage. Typically, when we're doing complex power conversation, we like to use effective, but you could use maximum as well. It would be V of maximum square root of 2 as well, if that's what you prefer to use or you need to use. So now, how do we relate complex power back to here? But we know that complex power is real power plus J reactive power. And we furthermore know what the values of real power is, because real power is basically Vm Im divided by 2 times cosine of theta b minus theta I. And we know that the reactive power is the same, almost the same, Vm divided Im divided by 2 times cosine of theta b minus theta I. Now, if we take this, we can expand it out and factor some is Vm Im out of here divided by 2, and what we are left with, we would be left with cosine of theta b minus theta I plus j sine of theta b minus theta I. Now, if you recall, there is a identity called Euler's identity, which is very useful to working on these kind of problems. Which all it says, Euler's identity says, if you've got e to the j a, then you can write it also as cosine of a plus j sine of a. In a sense, if you look at this thing, this is really going between polar and rectangular coordinate. That's where Euler's identity is. So if you're going to take this and look at this, we can go ahead and write S as Vm Im divided by 2, and we can write that one as Ej theta v minus theta I. Okay, and then doing some cleanups. So a way of thinking about this, I can then write V of m s as Vm Im over 2 with a phase angle of theta v minus theta I. That's kind of interesting. So now we can, oh, by the way, we can also, if you prefer, you can just say V effective, I effective, angle of theta v minus theta I. That's a good thing to have available to you to use. And there are many different ways of dealing with that. We could also, for example, take this and break it open to V effective, e to the j theta v, and then multiply this piece multiplied by I effective, e to the minus j theta I. So this is really basically the vector V effective, and this is the vector I effective. So we could just simply write it as V effective times I effective, but remember there's a minus j. This is usually represented with conjugate. this star is not anything. This is a conjugate, and conjugate of a function is where j gets replaced by minus j. So see there's a negative sign here, so I effective would have been I effective magnitude e to the j theta, but it was minus j just to become. So you got to be careful with that when you're working with the phasor domain. So we got a bunch of these things, and we can actually start introducing, because we know that z in phasor domain is v effective over I effective, right? So if we know that, then we can come up with a whole bunch of variation. And I'm not going to go through all the variations of this, but you can, for example, you can take this, apply it there, and say S is equal to, I could replace, for example, V effective with Z I effective. So I can say Z I effective I conjugate. That's another way of writing S. These are multiple ways of writing S. Most of them are derived from just basic ideas behind the definition of Z and the complex number rules. The other way would be I can take I and replace it with V effective Z. So I could write this thing as S is equal to, but remember it's conjugate, I conjugate, so if you're going to replace I conjugate, we have to conjugate the whole thing. So it would be basically V effective times V effective conjugate divided by Z. So those are some Z conjugate actually, because I was conjugate. So these are some of the different ways that we can relate power to the circuits we have, and be able to deal with it. So these are so let's go back to the beginning. So if you have a circuit, and it's the circuit, you know what the vector I effective is and the vector V effective is, and you know the Z, you can calculate the power using one of these later equations that we derived here. That brings us to the end of this video, talking about relating complex power to phasor domain voltage, current, and impedance.